So the plan is to define a certain infinite dimensional Lie algebra, talk about one of its representations, and give the axioms of vertex algebras, and then discuss why this representation pi has the structure of a vertex algebra. And the point of this talk is to prepare us for talks by Anthony and Josh in the coming week, where they will show that this Heisenberg Lie algebra acts on the direct sum of the cohomologies of the Hilbert schemes of n points of X, and that this makes this cohomology isomorphic as a representation to the Fock space, which means that it becomes a vertex algebra. And this is a famous result of Nakajima and Granovsky. So I found this on Math Overflow and it made me laugh. So Vivek Shende posted, why do we care about Hilbert schemes? And in particular, a question that he asks is, what can someone who knows a lot about the Hilbert scheme contribute to other areas of algebraic geometry or mathematics? And Nakajima wrote, I know a little about the Hilbert scheme, and I have no contribution to mathematics, but I find the study of Hilbert schemes is very interesting. Isn't it enough? And Richard Thomas wrote, -1 mark for excessive modesty. And then I blocked out this bit, but Nakajima also wrote, if I am asked this question by a politician, I will answer differently. So, anyway. Okay, so now we're going to define this Lie algebra. So we start with a lattice, which is a finitely generated abelian group with a positive, definite, symmetric bilinear form. And so a nice simple example that we can keep in mind is a rank 1 example, where gamma is the square root of n times an integer, and the pairing is multiplication.
Emily, you've got a question from Elijah in the chat. Torsion free?
Yes, sorry. Thanks. Okay. And then we associate to gamma a commutative Lie algebra of rank, whatever the rank of gamma is. And we call it H, because now it's a Lie algebra, but it's just the vector space spanned by gamma with the 0 bracket. And we consider the loop algebra, which just means the Laurent series with coefficients in H. And so this is spanned topologically by elements that look like alpha tensor T to the n, where alpha is an element of the lattice and n is an integer. So we might need infinite sums of these guys to give an element of the loop algebra. And we observe that we can extend our bracket linearly to H. And now we can define the Heisenberg Lie algebra, which is H hat sub gamma. This data of gamma and the pairing, and it's defined as a central extension. You have a living inside of our Lie algebra, and it's an extension of the loop algebra. And so the vector space is the direct sum of this piece and this piece, and we need to say how to bracket elements together. And so it's central, which means that one commutes with everything. And so the only question is if I have two elements of here and they lift to something in here, I bracket them together. When I project back down, I should get the old bracket, which was 0, but I could get something else, some scalar multiple of this thing. And that is exactly what we want. So if I have an element like this in the loop algebra, and I want to take the Lie bracket with another element, then in the loop algebra, these bracket to 0, but in the Heisenberg, we take the pairing of alpha and beta, and then we take the residue of f dg, and then, so that gives us a complex number, and we scale 1 by that number. And so here, so the residue of ht dt, so I should really be writing the residue at t equals 0, but we'll never take any other residues. So the convention is to be a bit lazy. And that's the coefficient of -1, where h of t is a Laurent series. Okay, and so it's a not terribly hard exercise to show that this satisfies the axioms of a Lie bracket. And as an example, let's work out what happens when we deal with the special case that f and g are monomials. So we want to take the bracket of alpha tensor t to the m with beta tensor t to the n. And that tells us the definition that we just made says we should pair alpha with beta, and then we should take the residue of the product of tm and n tn minus 1 dt. Okay, so this is just the residue of n t to the m plus n minus 1 dt. And this will be equal to 0 unless m plus n minus 1 is equal to -1. So, and if it is equal to -1, then we just get an n. -1 and 0 otherwise. So this is the same thing as saying that m is equal to -n. Okay, so in fact, the Heisenberg is not so far from being commutative in that almost all of these generators will commute with each other, except if m and n are, one is minus the other. So what we see is that Heisenberg is topologically generated by elements alpha n, which are going to be our shorthand notation for alpha tensor t to the n, where alpha is in gamma and n is an integer, and 1 satisfying the relations that the alpha n's commute with 1, and we just calculated what happens when we bracket an alpha n with a beta m. So we get minus alpha beta times n times the delta, Kronecker delta. So it's And we can, because m is now equal to minus n anytime this is not 0, we can replace the minus n by an m. So we don't have a sign. Okay, so that's a presentation by generators and relations.
Emily, you switched the n and m from your previous calculation. So,
I did. Thank you. That fixes it, right? Okay. And so I've been kind of throwing this topologically generated around casually, so maybe I should say a little bit about the topology. So here the topology on the Heisenberg is determined by T. So it has a basis of open neighborhoods of 0 given by t to the n times the polynomials. And we can see that the bracket is continuous with respect to this topology, and so we have a topological Lie algebra. And so when we study the representation theory, we're interested in representations which respect this topology, so we're interested in representations of the Heisenberg, which are continuous with respect to the discrete topology on the underlying vector space. So I thought I would just review what that means. So it means that the action map should be continuous. And because V is discrete, it's enough to check that for fixed vectors, B, then the map that is act on V, let's call it gamma V, should be a continuous map. Okay. And now because V is discrete, there's a lot of open sets. In particular, this guy is open. And so if gamma V is a continuous map, then the pre-image should be open in the Heisenberg, which has a more interesting topology. And we have a base of open neighborhoods, and so for this guy to be open, we need that it contains one of those distinguished open sets. So that just means that there exists an integer n such that t to the n times h of square brackets t times v is equal to 0. Or let me be more. I wanted to do that in one more step. So this should be contained in this thing that I said is open. And what does it mean for that to be contained? It means that for all that there exists an n sufficiently large such that t to the n kills v. And this should be true for all B. So let me highlight this because this is our definition of a continuous representation. Okay. So a remark is that instead of studying this guy with its continuous representations, we could study this guy with ordinary representations, and then we don't need to worry about having needing infinitely many basis elements in a sum and things like that. And the reason that I've chosen to focus on this one is because it reflects the geometry of what's going on more accurately. So geometrically, this is the only specs that are going to appear in this talk. There's something going on involving the punctured disk, which is spec of Laurent power series, and not C star, which is spec of this guy. And one particular feature that we get when we use infinite sums is that it's independent of the coordinate t, which is useful if you want to do geometric constructions. So we may get to that in future lectures, so I thought we should just introduce all the terminology now. Okay, so now we have to be a little bit careful when we talk about the universal enveloping algebra because we want to take in the topology into consideration again. So if we just take the universal enveloping algebra by taking the tensor algebra and quotienting by the relation that we want, then this contains finite linear combinations of finite products of possibly infinite sums of the generators alpha n. And one, there's a one going on too. And so if we take the topological completion, we should consider infinite sums here, and that means that we don't need to consider the infinite sums here. We can distribute out. And so the topological completion, which I'll denote by putting a tilde, so we have a tilde and a hat, is spanned by infinite linear combinations of finite products of alpha n's and one. Okay, and so we'll work with this because even though it's bigger, it's easier to identify a thing that is in it. Okay, and so we have a Pbw theorem as well in this case, and it says if we take a basis of gamma, so that is going to give a basis of H, then a topological basis of H hat was given by alpha i's tensor t to the n. And so now topological basis of the universal enveloping algebra is given by monomials, which are a pain to write. So, oh, still wrong. Go. So I have alpha 1 and 1, alpha 2, nope, still alpha 1. Oh, I need more notation, that's why. Okay, alpha 1 and 1, 1, alpha 1 and 2, 1, alpha 1 and let's say K1, 1. Okay, so all of these guys have the same alpha 1, but they have different powers of n, and we can assume that n1, 1 is less than or equal to n2, 1. Like this. So this is ordered. And then I start looking at alpha 2, so now I have n 1, 2, and so on. Does this make sense? So I have monomials in infinitely many variables.
Sorry, what happened to boldface 1? Is that in there as well? Or?
Oh yeah, probably. Yeah, but I'm very soon going to quotient out by that, so I was not careful. So a continuous Heisenberg representation in the way we discussed above is equivalent to a representation of this topological algebra. Probably continuous. Okay. So just like we do with finite dimensional Lie algebras, we'll talk about representations of the one and the other, and we won't be very careful about what we mean. Okay, so now let's talk about the action of this central element. So if we have an irreducible module, the action of one, because one commutes with everything, we get this act by one map, which goes from V to V and sends V to 1 times V. And this is a morphism of representations because one is central. Okay. So in particular, it's a linear map of complex vector spaces. So we can find an eigenvalue. So let's let V0 be an eigenvector with eigenvalue kappa. So we're saying that 1 times V is equal to just scaling V by kappa. Then if we consider this gamma 1 minus kappa times the identity, which sends an, well, these should be V0s, but now the general element V goes to 1 times V minus kappa of V. So this is still a morphism of modules. And the kernel is not 0 because V naught is in the kernel. And so by Schur's lemma, which says that a map between irreducible modules is either an isomorphism or 0, this is 0. So the conclusion is that if B is an irreducible module, then one just acts by some scalar. There exists a complex number kappa such that 1 V is equal to kappa V for all V in V. And so we have a term for this. We say that V is a representation of level kappa. And so we're going to fix it.
Sorry, you didn't assume that V was finite dimensional, did you?
No, that's true.
So in principle, the central element doesn't have to have an eigenvector at all.
Mm-hmm. What's the name of the lemma that we use, Anna?
Dixmeyer's lemma?
Yeah. So you need at least countable dimensional.
Yeah, you need some assumptions on the vector space.
Okay. Thank you. Okay. So anyway, what we often do from now on is that we only study representations of level K. And such a representation doesn't need to have any restriction on the dimension. It just has the property that 1 acts by K all the time. And representations of level K are equivalent to modules over the quotient of the universal enveloping algebra, where we require that 1 act by K. And a remark here is that any choice of kappa, which is non-zero, gives an equivalent theory. So you could just rescale everything to change your kappa. And this is different from the case of affine algebras, where you get very different representation theory when you change the level.
Is this, Emily, is this because of these universal enveloping algebras look the same, like these quotients? Because what happens for affine algebras is that sometimes they gain a center.
Mm-hmm.
And does that just like not happen here?
Yeah, it just doesn't happen here. So I can just rescale alpha n by like kappa to the 1/2 alpha n. And this gives an isomorphism and it changes the level.
Okay.
Something like this. Okay, so that's the Lie algebra and the related associative algebras that we care about. And so since it doesn't matter what level we take, as long as it's not 0, we're just going to take 1. But the theory would be equivalent if we scaled. And so now our goal is to construct a possibly understandable module. So construct a module of level 1, which is as small as possible. And a remark is that we can't have any trivial representation, so no representation of dimension 1. So suppose that we did have a dimension 1 representation, then our generators would act by scalars. So let's suppose that we have alpha, a non-zero element of our group, and n, a non-zero integer. And suppose that we knew that alpha n acted on an element by a scalar, and alpha minus n also acted by some other scalar. Then acting by scalars commutes, so alpha n times alpha minus n acting on v is lambda mu v minus mu lambda v, which is 0. But on the other hand, this bracket is supposed to be n times 1 acting on v, which should be n times v. And so this is a contradiction. So there's no representation this small. But if we just consider H plus, so the algebra generated by alpha n's where n are positive, these all commute with each other because we're never going to get n and minus n bracketed together, which was the only time things didn't commute. And so we do have a trivial one-dimensional representation here. The we can define a trivial representation of the subalgebra on C, and then we can induce this representation to the whole thing. And so we're going to call this pi. And so this is the tensor product. And this is called the Foc representation. So how can we think about it? So there's kind of an analogy with Verma modules. So let's remember what we know about Verma modules for a semisimple Lie algebra, G. So let's write G as n minus plus h plus n plus, and this will be our Borel. And so the analogy that we should keep in mind is that these are going to be the alpha n's for n positive, and these are going to be the alpha minus n's, and this is going to be 1. So this is the analogy. And so what we did already was we fixed a level. We said how 1 was going to act, and the finite dimensional analogy of this is that we fix a character. And then we let n plus act trivially, so by 0. And we extend to an action of B using lambda. And then we induce to all of G. And then we get the Verma module and lambda of highest weight lambda. And again, we have a nicer Pbw theorem with finitely many variables. And it tells us that, in particular, UG is isomorphic as a vector space to the tensor product of U of each of these subalgebras. And because these are all commutative, the universe enveloping algebras of all of them are just symmetric algebras. And so we can see that when we take the induced module, we get from that M lambda is isomorphic to UN minus as a vector space, meaning that it's a polynomial algebra on C alpha I, where let's call them alpha I minus, where these form a basis of N minus. And then once we know that as a vector space, we can say how the action of G on M lambda is given by saying how each of the parts act. So N minus acts by left multiplication. And as for H and N plus, we use commutation relations. To move elements of H and elements of N plus past elements of N minus until we get them all the way to the right, and then we remember that H of 1 is equal to lambda h, and x of 1 is 0. So everything is very analogous.
Sorry, can I just interrupt? One difference between the two situations is that in the Lie algebra, n minus is not abelian. So, I mean, the universal enveloping algebra of n minus is the polynomial ring as a vector space, but not as an algebra.
Mm-hmm. Yeah.
So when you said that n minus acts by left multiplication,
yeah.
I mean, if you want to put it back in terms of the Pbw basis, that you're still going to have to use some commutation relations.
Yeah, thank you. I was sloppy. Okay, I think I have no longer said anything false. Yeah, okay. But in our analogy, we don't have this problem, which is why I forgot about it. So we see that pi as a vector space is a polynomial algebra on infinitely many generators, alpha I to the n, where alpha I and gamma form a basis of H, which was this guy, and n are negative. So and now the action, again, we're going to say how the sort of negative part behave. So alpha i's ends with n less than 0. Now it really just is left multiplication because they all commute with each other. So I can just change the degree of my polynomial as necessary. The alpha I n, where n is positive, again, this is determined by the commutation relations, and then observing that once I get to 1, then I get 0. But actually, we can recall how the commutation works, and actually, alpha I n acts on a monomial as n times the partial derivative in the variable alpha I minus n. And alpha I of 0 is 0. And of course, the first thing that we said was that we were going to make this be 1. Okay. So an exercise is that this is an irreducible highest weight module with highest weight vector 1. I guess not bold 1, just ordinary 1. Okay, and now we can say fun physics words and sound like we know what we're talking about. So this highest weight vector 1 is called the vacuum state. The operators alpha n, where n is negative, are called creation operators. And they're called that because each alpha n creates the state alpha n, I'll say more about that in a second, from the vacuum 1. So here, this alpha n is an operator. I'm viewing it as an element of the Lie algebra. And this alpha n is a state. I'm viewing it as an element of pi. So the vacuum, there are no particles here and there is one particle here. So a particle has been created. Okay, and then the alpha n's for n positive are called annihilation operators. And the idea is that if you apply this enough times, if you take the derivative here enough times to any monomial, you will get 0. So if you enough times to any vector in pi, you get 0. Okay. And so being slightly sloppy with the notation, since pi is a polynomial algebra, we have a degree 0 piece, and then we have a degree n piece spanned by the negative guys, which I'm going to denote by n minus just temporarily. And then we have a degree 2 piece, and so on. And so this is where the vacuum state lives. And these over here are one particle states. And over here we have 2 particle states. And so on. Okay. And here is a super remark, meaning that if instead of starting with gamma and then the vector space that we get by tensoring over C, we start with a super vector space, which is a direct sum of an even part and an odd part, and we require that our pairing be graded commutative instead of symmetric, then we get a Heisenberg super Lie algebra and a Foc representation, and we just need to insert signs correctly. So now we need to learn what vertex algebras are, and I have to admit that I have never given the definition of a vertex algebra in a talk. I have always glossed over it because nobody wants to look at all the technical details, but I guess we do want to look at all the technical details because we actually want to understand the axioms a little bit. So here we go. So a vertex algebra consists of 4 pieces of data. The space of states. So we've already seen a space of states, so that's promising. And so the space of states is a graded complex vector space. V and each of the pieces should be finite dimensional. We want a vacuum vector. We've also seen the word vacuum appear, and that is some vector of degree 0. We want a translation operator, which is an endomorphism of V, which is linear and of degree 1. And then we want vertex operators, which we keep track of like this. So it's a map that goes from V to power series, TT inverse with coefficients in the endomorphism ring of V. So what I mean is a vector A in V goes to a formal sum of endomorphisms. And it is conventional to index them like this. So A sub round brackets n is the coefficient of z to the minus n minus 1. And we'll kind of see in a minute why. And so A sub n is a linear map. B to V. And if A was a homogeneous element of degree K, then we want A sub n to be a homogeneous element of the endomorphism ring. So we want it to have degree K minus n minus 1. So that minus n minus 1 is or minus n minus 1.
Should
So,
you be z's somewhere? Or your z's be t's?
Yes, thank you. And that's ugly.
And also, do you have any explanation for the funny notation in your vacuum vector? This bracket catch notation?
Yeah, that was all I was going to say.
Yeah, but why do we want it to have that, to look like that?
Oh, well, sometimes you get other things and you want to pair them. And it is going to fit together nicely like that.
Okay.
Pretty. I don't know. Does anyone else have a better explanation?
Yeah, I always thought it was just that yeah, in order to put covectors and vectors next to each other and make it look as if you designed it from the beginning.
Okay, so that's the data. This is called the state field correspondence. So these are states and these are fields. And these data are subject to a bunch of conditions, and in a research talk I would say a bunch of boring conditions and skip them, but now we need to know what they are. So the vacuum axiom says if we plug in the vacuum to our vertex operator gadget, in principle we get an infinite sum with infinitely many operators, different degrees, but in fact we only get one is the density. Okay, and you can check if you like that this has the correct degree. And then the second part of the vacuum axiom says, what if I plug in an A here, get a bunch of endomorphisms, and then act on this vacuum vector? So it says that for all A in V, if I look at A sub n, which is an endomorphism, and I act on 0, then if n is positive, I get 0. So this is kind of nice. This reminds us a little bit of our annihilation operators, which were indexed by positive integers and killed stuff. And what else happens is that A of minus 1, so that's the first thing that could be interesting. And we apply that to 0 and we get A out again. So if we collect this information into our sum, so YA of Z acting on 0 is in principle this infinite sum of AN acting on 0 times Z to the minus n minus 1. But in fact, we only have to look at negative Zs, which means negative n's, which means positive powers of Z. And we have A times Z to the 0 plus A minus 2, 0 times Z, and so on. And so what we see is that we have a constant term of A, and then we have only positive powers of Z. Okay, so that's an axiom about the vacuum and how it interacts with the vertex operators. And now we have an axiom about how the translation operator interacts with the vertex operators, which says that if we commute the translation operator with this sum of operators, that is the same thing as taking the derivative of this whole sum with respect to the variable Z. And that is the same thing as applying y to ta. And this is for all a in v. Okay, so let's expand a little bit what this first equality tells us. So we have a sum over z of t composed with a sub n minus a sub n composed with t times z to the minus n minus 1. And to start, equal to partial derivative of the sum n z to the minus n minus 1. Okay, and so we can calculate this. This is the sum of minus n minus 1, a sub n, z to the minus n minus 2, and then we can make my discrete math students change the index because it's good practice for them. And so we get minus n, a, n minus 1, z to the minus n minus 1. And so what this tells us is that the bracket of t with a sub n is minus n t minus n times a to the n minus 1. And if I also consider this part, then this is also equal to t a sub n. Okay, so really this axiom could be viewed as a whole collection of axioms like this, indexed by n's. And the second part of the translation axiom is more straightforward. It just tells us that if we act on our vacuum vector, we get 0. Okay. And then we have the locality axiom, which is some kind of commutativity constraint. And it says that for any two vectors, a and b, there is some positive integer such that if I multiply by this high enough power of z minus w and I compare the composition of ya with yb, it commutes. So this should be equal to 0 as a formal sum with coefficients in endomorphisms in the variables z and w. Okay, so this is maybe the most confusing looking axiom at first. And so here I'm going to try to give some intuition about it. Okay, so the first observation to make is that in principle, YAZ could have infinitely many positive and negative powers, but because the grading on V is bounded below, when I apply to an individual vector of V, I only have finitely many negative powers. So let me write that. For any V in V, when I apply this sum to V, I land here, Z again. Here, let me emphasize that this means that the negative powers are bounded below. Okay. And let me, this is not very rigorous, but let me for simplicity just assume that V is C because I don't want to worry about tensor products of things with infinitely many sums. So then if I take this guy, which is in here, And now I apply YB to each of the terms in the sum. Then this is in this subring of the possible place I could land. Okay. And if I do it in the other order, then I land in a different subring. And if we tried to insist that these operators commute, then that would mean that I always need to land in the intersection of these two rings. Which is a pretty strong restriction. And in fact, it turns out in combination with the other axioms to be an even stronger restriction. In fact, there cannot be any poles at all. So let me explain why. So I'm taking two vectors, and I'm taking y, a of z, and I'm applying it to b. And now I'm going to rewrite b using my vacuum axiom, which says that b is the first term when I apply yb to 0 to the vacuum vector. So this is y, a, z, y, b, w applied to 0, restricted to w equals 0. And so that's pulling out the constant term of this sum, which we know is b. But now I'm going to use that we just said that these should commute. Okay. And so this should be y, b, w, y, a, z of 0. Okay. But now by the vacuum axiom again, this guy here has no negative powers of z. And then we're setting w equal to 0. So there's no w's involved. So this entire expression here has z's in it and no negative powers. And so it actually lives in here. And so if we required that all of our vertex operators commuted in this strong sense, then actually there would be no poles at all. And we'll see in a minute that this makes a pretty boring vertex algebra, and we wouldn't need the machinery of vertex algebras for anything. Okay, so we don't want to require that they actually commute, but we weaken it a little bit to get the locality axiom, which means that they commute after we multiply with a big power here.
Emily?
Yeah.
So what is the difference between v double bracket w, then double bracket z, and then the thing below?
Yeah, okay. You have to be very careful with these things, but this is saying that I can have, so if I call this double, let's not, why, I lost the page. If I call this, it's a good name for a vector space. It's not V or W. I don't know. Let's call it U for a minute. Then what is U of round bracket Z? It's finitely many negative Zs, but infinitely many positive Zs. But in each of those infinitely many positive Zs, I have an element of here which had finitely many negative W's. And so the kinds of poles that we can get in W are different than the kinds of poles that we can get in Z, and conversely. So if you read vertex algebra books, there's much discussion of these technicalities. Yes, but the point is that we don't want this condition anyway. So, yeah. Sorry. Okay, so let's look at our first examples of vertex algebras. So we construct them starting with a graded commutative algebra with a derivation of degree 1 and a unit, which we will call 1. Then we can make this V into a vertex algebra by taking the vacuum to be 1, and by taking our vertex operators to be given by multiplication by this guy. So what does this mean? It's the sum over positive integers over multiplication by t to the n of a divided by n factorial, and then z to the n. Okay. And so if we change our indices, we can see that a sub n, so that's supposed to be the coefficient of z to the minus n minus 1 is equal to t to the minus n minus 1 times a over minus n minus 1 factorial if n is negative and 0 otherwise. Okay, so we can check some axioms. So if we take this exponential involving our vacuum, which was our identity element, the ring, unit, and we apply the derivation n times, and take the divide by n factorial. Okay, but when you apply a derivation to the unit, you get 0. So this is 0 if n is at least 1. And so the only term we have is when n is equal to 0. And then we just get multiplication by 0, or by the vacuum. Okay, but the vacuum was 1, so multiplication by 1 is the identity. So that's our vacuum axiom. And our other part of the vacuum axiom said we should expand this and we should get something which has no negative powers of z. Well, we never have negative powers of z in this vertex algebra. And the leading term should be an a. And so we can check that pretty easily. And so we're going to take this guy and multiply, act on this one, but this is 1. So we don't change anything here. And so I sum like this. And when we expand, the first term is a, and then we have higher order terms. Okay. So that's our vacuum axiom. We can think about the translation axiom as well. And remember that this is what it meant for individual coefficients. So if I look at this and I apply it to a vector v, I want it to be the same as applying this guy to that vector. So what do I have here? I have t applied to t to the minus n minus 1a over minus n minus 1 factorial times b minus t to the minus n minus 1a over minus n minus 1 factorial t to the b. And you can see that you're just going to use the product rule here. And you're going to apply t to this term, or you're going to apply t to this term. And when you apply to the second term, it's going to cancel what you have over here. And so what we get left is t to the minus n over a times minus n minus 1 factorial times b. And then you can massage this a little bit, pull out the minus n, and you get what you wanted. Okay. And the locality axiom is actually immediate from the commutativity. So in fact, we have the stronger condition that we said was too strong in general. So in fact, you can show this easily. And when this holds, we say that V is a commutative vertex algebra. And conversely, for any commutative vertex algebra, we saw that we have no poles at Z. And so the claim is that we can make V into a commutative algebra with derivation. And here's what we do. I define M sub A to be the linear operator, which is A sub minus 1. So this constant term. Of our vertex operator. And I define this thing that's going to be my multiplication to be M applied to B. And it's not hard, so that's an element of V. And the fact that Y AZ applied to Y BW is equal to Y BW applied to Y AZ, that you can deduce from that by looking at the constant terms that you have a commutativity here. And you can also deduce associativity from this same thing. So I'm going to apply it to a third vector, C. And so that tells me that MA of MB applied to C is equal to MB of MA applied to C. Okay, and now I can combine this fact here together with this fact here to get associativity in some kind of way. I don't know if I did it the most efficient way, but here is a way. Okay, so here I have just used commutativity on the B and the C, but now I'm going to use commutativity on this entire factor with the A. So I have C star B star A. And now, what did I do? No, okay, my proof, it does not work. I see. But there's something along these lines that should work. I should just move brackets around. I think, sorry. I think that at this stage, I should swap the role of A and C using this rule here. Yes, this is better. And then I can commute again. So this is a small algebra exercise that I think is correct now. Okay, and so what we get is that V is a commutative algebra with derivation. And the conclusion is that a commutative vertex algebra is equivalent to a commutative algebra with derivation. So those are our first examples, and the next example is the Heisenberg. Are there questions so far?
I guess there's more to show in that conclusion, because you need to know that the rest of the vertex algebra structure was the one that came from the derivation.
Mm-hmm.
Yeah, that's fine.
Okay. So the next claim is that this Foc representation pi has a natural structure of vertex algebra, and it is called the Heisenberg. Vertex algebra. To L. Okay. So why is this true? And the general proof, so I'm going to focus on the rank 1 case, just because I'm tired of drawing indices on my alphas. But the proof is not different in the general case. I just only wanted to work with one alpha. Also, this is called the rank 1 free boson, which is fun to say. Okay, so we need to give all of this data. And the first data that we needed was a space of states, and that is going to be our vector space. And now, because we only have one alpha, the monomial is like this, which is a little bit of a headache to write. And our space of states was supposed to be graded. And I want it to be positively graded. So I'm going to set the degree of 1 to be equal to 0, and the degree of alpha j to be equal to minus j. And so that means that a monomial like this guy has degree minus the sum of the ji's. So it's kind of interesting to notice that there are several. You could also naturally grade it by making each of the monomials have degree 1, and then you'd be looking at the degree of a polynomial. So there are several gradings that happen, and we'll see that appear a bit later at the very end if we don't run out of time. Okay, so that's our vector space. The next piece of data we need is a vacuum vector, which should have degree 0, and we take it to be 1. And the last piece of, no, not the last, second last piece of data is the translation operator, which should have degree 1. And I'm going to define it inductively by, well, first of all, we know from the vacuum axiom that when t acts on 1, it should be 0. And then I'm just going to tell you how it commutes past alpha j, and that is minus j times alpha of j minus 1. So this has the flavor of taking a derivative a little bit. Okay, and remember that j is negative, so this is a positive scalar. Okay, and so then because everything is written by multiplying 1 by these guys, and I know how to commute past, then that determines everything, and you can just show inductively that if you act on a product, then you get a sum. So this is kind of a product rule. And for each term in the product, you get a scalar, and then you've subtracted 1 from the integer there. Okay. So that defines a translation operator, and it has degree 1. And so now the big question is, how do we define vertex operators? And we approach this cautiously, beginning with the simplest possible case, which is our degree 0 guy. Well, we're told from the vacuum axiom that this has to be the identity. So step 1 is done. And step 2 is the next simplest guy is this degree 1 term. So our degree 1 part has dimension 1, it's spanned by this guy, and we want to know what endomorphisms we should assign to it. And a remark, is that every vector in pi, once we've made this definition of t, every vector in pi can be constructed by acting on 1 by alpha minus 1 a bunch of times, viewed as an operator, and applying t. Because t will take alpha 1 to alpha minus 1 to alpha minus 2 and minus 3 and minus 4 and so on. So we get all of the big negative values of j, and then we get products in this way. And so in a certain sense, alpha minus 1 and t know everything about the representation. And so defining y alpha of minus 1 is the key step. So we shouldn't feel like, I don't know, I told you how to define it in degree 0 and then degree 1, and you're going to say, are you going to have to do it degree 2, degree 3, degree 4, we'll be here forever. And the answer is somehow that once we've done this, we're basically done. And this is a theorem called the Reconstruction Theorem, which is basically some kind of idea of generators and relations for vertex algebras. So if you have things which generate in a certain sense, and you define the vertex operators and they satisfy appropriate relations, then you've defined everything. Okay, so we don't know what it is yet, but it's going to just formally look like this. Okay, and rather than writing alpha minus 1 sub n, I'm just going to use the notation alpha sub n for a minute. So I defined it in notation. N is a map to pi, and it should have a degree equal to the degree of alpha minus 1 minus n minus 1, which is minus n. Lost something. Okay, so we don't know what alpha n is, but it should be an endomorphism of degree minus n. And so there is a natural guess, which is multiplication by alpha of minus n. And I claim that this guess works. So we're going to set it to be equal to this. So that alpha sub n was very temporary. Okay, and an observation to make is that this is a generating function whose coefficients give us the generators of our algebra H, which was the quotient of the universal enveloping algebra. And so because it's a generating function, we're going to denote it by alpha of z. So we can view these guys as elements of H, or we can view them as linear operators by remembering that they act on pi. Okay, and so the claim is that this determines everything. So for example, if we want to know the vertex operators for alpha of minus 2, we just observe that alpha of minus 2 is t of alpha of minus 1, which tells us that the vertex operators are given like this, and then we use the translation axiom, which said that we can take the t outside of the brackets if we change it to partial derivative by z. Okay, and so we do that, and we get a sum minus n minus 1 of alpha minus n z to the minus n minus 2. Okay. And inductively, you can show that for any k, what I get here is going to be 1 over k minus 1 factorial, and I'm going to take the derivative k minus 1 times. And you can calculate what that is. Okay, so all of the high powers, the high values of alpha, we can deal with, but the question is how do we take products? So what about alpha minus 1 times alpha minus 1, which is a degree 2 thing in pi? And so the most naive guess would be, let's just multiply those power series. Okay. So we know how to multiply formal power series. So the coefficient, we look at k plus l, pairs which sum to n, and we have alpha minus k, alpha minus l, and that's the coefficient of z to the minus n minus 2. But there's a problem here because k and l are allowed to be negative. So there could be infinitely many choices of things here. And so we have an infinite sum in principle. And so we need to check if this sum is still well defined when we're acting on pi. Okay. So we make some observations. The first is that if minus L is positive, then this guy is an annihilation operator. And it's the thing that's acting first, and it's going to kill a lot of stuff. So for any v in pi, all but finitely many of the annihilation operators kill v. So v is a monomial, and the annihilation operators for terms L that don't appear in that monomial will commute past all of the terms and hit the 1 and kill it. So it's only the creation operators that appear in this, let's say, monomial. It's a sum of monomials. So, and only the annihilation operators corresponding to finitely many creation operators, which appear in here, don't kill it. So infinitely, most of them do. And likewise, if k is positive and the sum of minus L and minus k, which is equal to minus n, is not 0, then we can commute the alpha minus k past the alpha minus L. So and so now we again have an annihilation operator acting first, and most of them kill v. Okay. And there are only, for a fixed n, there are only finitely many pairs minus k minus L with both less than 0, less than or equal to 0 for fixed n. So as long as n is not 0, then we only get finitely many terms here and finitely many terms here and finitely many terms here, and this covers all cases. So as long as n is not equal to 0, when we act by this sum, even though the sum has infinitely many terms in it, this is a finite sum. Okay. But if n is equal to 0, then we can't do this second step, and so we have a problem. So for example, for any k, which is positive, I can look at alpha k, alpha minus k, acting on 1. And this is, well, if we remember that alpha k, when k is positive, is k times the partial derivative of alpha minus k, of alpha minus k of 1. And so we're creating something, and then we're taking the derivative. And so we're getting the sum over k of k times 1. And so this is bad. So when n is equal to 0, we don't get a well-defined linear operator, and so we cannot make this definition. We can't say that these are the coefficients of our vertex operator. But the observation is that if I could swap the order of these and have this guy act first, then I wouldn't have this problem. The problem is that it's coming right after the thing that created the thing that stops it from killing the vector. So the observation is that if we could move the annihilation operators to act before the creation operators, we wouldn't have a problem. Okay, so the new guess is just to force this to happen. And this is not a natural thing at all. And so we have to invent new notation. So we take the sum as before, and now I look at the two operators, alpha minus k and alpha minus l, and I swap the order if necessary. So I put these two dots here. I'll write that down in a second. And so this is the coefficient of z to the minus n minus 2. Did I change my signs? No, okay. And so what this notation means is it's alpha minus k, alpha minus l, if minus l is bigger than minus k. And if not, we swap them. Okay. And so I'm always getting the most positive thing to the farthest right. And this is called the normally ordered product. And it is not a very natural thing to do. It's not associative in general. It's not commutative in general, but it works. And we also adapt that notation over here. When I take the normally ordered product of all the coefficients, then I also say that I've taken the normally ordered product of the fields, of the sums. Okay. Okay, so let's think a little bit about what that means we've just defined. Well, when n is not equal to 0, these two things are equal anyway. They commute, so it didn't matter that we put these dots. So in the case that n is not equal to 0, we still just get this sum because we can commute them back again. But in the case that n is equal to 0, we need to split the sum. So let's look at the cases where k is greater than 0. We have alpha minus k, alpha k, so positive guide to the right. And when k is less than 0, then we swap the order. Okay, and these sums look pretty symmetric except for this k equals 0 term, but remember that alpha 0 acts by 0. So in the endomorphisms of pi, the 0 term doesn't count, so we can just get rid of that. And so we get 2 times the sum over positive k's alpha minus k, alpha k, and if we remember how alpha k acted, we can write it. So this is how it acts on monomials. Okay, and so the facts are that this works. Okay, and the second fact is that, okay, we saw how to get a product of two things, and we saw how to get high j's. And remember that we got high j's by taking derivatives. And so we generalize this procedure. If we have a product of things with big negative j's appearing, then we do both procedures at once. We take derivatives, power, take the normally ordered product. And again, as I remarked, in general, this normally ordered product is not associative. And so it's just a convention that is widely accepted, as far as I can tell, that puts things more lots of colons, then you put the brackets to the right. But actually for the generators, it turns out to be associative. So we don't need to specify. Okay. So the upshot is that we get a whole lot of data that physicists get excited about, but it's all determined really. Okay, so I'm almost done, but I want to talk a little bit about the graded dimension because it will be relevant in the future. So again, a remark is that if we started, instead of our lattice, we started with a graded vector space with an appropriate pairing, and we carefully introduce signs, then we get a super vertex algebra. Fine. Okay, so let's just finish by talking about the graded dimension of this space. So this doesn't use most of the vertex algebra structure, but it does use the grading that I introduced. And so that's why I left it to the end. So if we have a graded vector space, we can study its Poincare series, which is a polynomial in Q, or a power series, where the coefficients are given by the dimensions of the nth graded piece. Okay, and so in our case, pi was a symmetric algebra, and so we can calculate its graded dimensions. So remember that it's a symmetric algebra on a vector space, which we can view as the direct sum over alpha i's for a basis and n's, which are positive, strictly positive, of a one-dimensional vector space spanned by alpha I minus n. Okay. And remember also that when we take the symmetric product of a direct sum, we get the tensor product of the symmetric products. So we get the tensor product over n's and the tensor product over alphas of a polynomial algebra on a single generator, which has degree n. So this thing here in degree 0 is C, in degree 1 we have an alpha I, in degree 2 we have 2 of them, and so on. And so the Poincare series here is 1 plus Qn plus Q2n, and so on. So we have nothing except in these dimensions where we have a one-dimensional space. And as my discrete math students should be able to tell us, this is this function here. Okay, and so now we're taking the product of this guy over all alphas, okay? But the dimension doesn't depend on alphas. So we're just gonna get a power of this to the rank of the lattice, and then we take the product over all n's. And so our Poincare series is the product over positive m's of 1 over 1 minus q to the m to the power r. Okay. And then in the super case, we can do the same calculation, except that instead of getting symmetric algebras, we get exterior algebras for the odd generators. So I'm going to assume that my basis spans the even part and the odd part, respectively. And so then my symmetric algebra, sorry, these are sums because they're inside. Okay, so it looks the same, but because this is, some of these are odd generators, then I get the tensor product over the symmetric algebra on the even part. And I also have to tensor by the exterior algebras on the odd part. Okay, and we already know how to deal with this guy. This gives us a 1 over 1 minus q to the n to the power r. And if we think about an exterior algebra on a one-dimensional space, then this has one piece in degree 1 and one piece in degree n. And so our Poincare series, I haven't left quite enough room, is the product over 1 plus q to the n times the dimension of h to the power of the dimension of h odd, and 1 minus q to the n dimension of h even. Okay. And there's one last thing to check, which is the case that we'll be interested in. So if H, which we said was a super vector space, is actually a graded vector space and that it's broken into odd and even parts according to the odd and evenness of the integers, then pi is bigraded. So we write, let's write in absolute values for the grading on H. So an element of pi, like alpha minus n, has degree n and the degree of alpha by degree. And so now we write pi as a direct sum over all of these pieces, and we can look at a generating function in 2 variables, which tells us the dimension of each of those pieces. And it's an exercise just expounding on the examples that I did to show that we get plus or minus depending on the parity. Why is there, I think this p should be a t. And it's either in the numerator or the denominator, also depending on the parity. So that is all, but we will see this polynomial again.